Good morning. We are going to start again with lecture number 12, continuation. And we are going to look at, rather recall whatever we had spoken about series resonance. And we will venture over to parallel resonance today. So let me start by sharing my screen. We had actually spoken about series resonance in the last class. So in series resonance, what we said was R, L and C will be connected in series. So we are going to have R, L and C, all of them connected in series, and they are connected to a voltage source, AC voltage source, which is of varying frequency. So we said that the impedance offered by the inductance will be J omega L, and the impedance offered by the capacitance will be minus J divided by omega C, and this is going to be R, and we are exciting the circuit with the voltage source which is corresponding to Vm sin omega t. So at omega equal to omega naught, we are going to have j omega L and 1 by j, rather minus j omega C, both of them cancelling with each other. So this is going to be essentially equal to j times 0. So omega L equal to omega C. This is going to be the condition for resonance. So 1 by omega C, I'm sorry, omega L equal to 1 by omega C. So we said that omega naught, which is corresponding to this resonant condition, which we call as resonant frequency. This is corresponding to resonant frequency. At resonant frequency condition, the impedance is going to be only resistive, purely resistive. And we are going to have the imaginary part. So the imaginary part of impedance, which is actually R plus J multiplied by XL minus XC or XC minus XL. This is going to be 0. So Z is this and the imaginary part is 0, and that is why we call this as resonant frequency. So if we say omega naught L equal to 1 by omega naught C, we got omega naught equal to 1 by root LC, which is the resonant frequency. Okay, so this is going to be equal to 2 pi F naught. So F naught is going to be equal to 1 by 2 pi root LC. So this is going to be the resonant frequency. Okay, so if we try to plot exactly how the impedance and the reactances change with respect to frequency. So if I call this particular frequency as omega naught, I'm going to have the impedance reaching its minimum value here. So this is going to be omega, which is less than omega naught, and this range is going to be omega greater than omega naught. So here omega naught L will dominate, not omega naught, omega L will dominate over omega C. So I'm going to have essentially under this condition, omega L will dominate. Whereas under this condition, we are going to have 1 by omega C will dominate. So if I look at the Z value here is going to be only equal to R at omega naught. Whereas here I'm going to have the net impedance Z will be capacitive. Whereas here Z will be inductive. Okay. Now V divided by Z is going to be I. So Here Z is larger. So if I'm looking at what is the Z variation, this is the variation of Z with respect to frequency. So if I am looking at the current value, which is V divided by Z, current value is going to be maximum when the impedance is minimum. So I'm going to have the current value somewhat like this. The current is going to be somewhat like this. This is the current value. So this is I max, whereas this is the way the current is going to change. So the current will increase to a maximum at resonant frequency. It reaches I max at resonant frequency, and it is going to decrease from I max in either direction. It is going to essentially come down. So I can say in one sense 1 by Z, which is actually admittance, which is specified by Y. Okay. So this admittance is exactly inverse of the impedance. So if I say impedance reaches minimum here, admittance is going to reach maximum here. So this can be the variation of both I as well as admittance. Both of them are going to reach maximum at this particular value of resonant frequency. Okay. And if I try to look at how exactly individual reactances change. So let me again draw with respect to frequency. If I say this is omega naught, if I'm going to have omega L plotted, so if I try to plot with respect, this is the direction in which omega is increasing. So if I'm going to have literally zero frequency somewhere here, as the frequency increases, I'm going to have this increasing like this. So this is the way omega L is going to increase, which is going to be XL. So that is proportional to omega, whatever is the omega value. Whereas if I try to look at what is the kind of variation we are going to have for capacitive reactance. So capacitive reactance, we said that Xc is equal to 1 by omega C. So when omega is 0, literally, we are going to have infinite value of capacitive reactance. And as omega increases further and further, and as omega reaches literally infinity, it is going to come down to zero. So I should show this capacitive reactance as though it reaches from a very, very high value and then it is going towards zero as frequency increases to extremely large values. So this is going to be the variation of Xc. How Xc changes, this is going to be the variation. Okay. So in general, we are actually looking at both XL and XC having the same value but of opposite sign when we are looking at the frequency being equal to omega naught. Now we also define one more thing called quality factor. So when I was defining quality factor in the last class, I had left out 2 pi factor. So the quality factor is defined as 2 pi multiplied by energy stored in the inductor divided by energy dissipated in R in the resistor for one cycle. So this is the definition of quality factor. So this can also be defined otherwise as the ratio of voltage drop in L divided by voltage drop in R at omega naught. So both of them we are talking about at omega naught. So this is going to be omega naught multiplied by L multiplied by I max. If I may call this as the maximum current that passes through the RLC circuit. And this can be written as R multiplied by I max. So we are going to have this as omega naught L divided by R. So this is going to be the quality factor. Now, we derived this expression in the last class using this particular definition of quality factor. I will just reiterate that. So that is going to be 2 pi multiplied by half L I max square, I peak square, whatever. So this is going to be I max square divided by energy dissipated is going to be I RMS square multiplied by R multiplied by whatever is one cycle time. And we already said that omega naught is going to be equal to 2 pi F naught, which will be equal to 1 by root LC, from which I should be able to write 2 pi divided by T is equal to 1 by root LC. So T can be written as 2 pi by root LC. Okay. So 2 pi by root LC is going to be T. So this can be written as 2 pi multiplied by root LC. That's what I was wondering, what mistake I have done. So this is going to be 2 pi multiplied by root LC is going to be T. So this I can substitute now. 2 pi multiplied by half multiplied by L. I max square can be written as IRMS multiplied by root 2 the whole square divided by I RMS square multiplied by R multiplied by 2 pi root LC. Okay. So by the way, root LC is 1 by omega naught. So I can write this as 2 pi by omega naught also. No problem. This can be written as 2 pi by omega naught. So now this 2 pi and this 2 pi will get cancelled. And this 2 and this root 2 square will get cancelled. This IRMS square and this IRMS square are going to get cancelled. So root LC is here, which is 1 by omega naught. So this is going to be omega naught L by R. That is what is quality factor. So this is going to be quality factor. Now, one more thing I need to say specifically is that if I am saying that the x-axis is omega and this is going to be omega naught, I am going to have the I max happening exactly at omega naught. So this is where I max is occurring. If I'm talking about this as I, so this is going to be I max. Now, at some point, the current drawn will become I max divided by root 2. Or I can say at this point, if I try to look at the power, what is the power? So P max is going to be I max square multiplied by the power delivered to the resistance under resonant condition. So this is the power delivered to R under omega naught resonant condition. Now at what point, at what frequency power is halved? Power becomes P max divided by 2. That's what we want to check. P max divided by 2. So if I say at what point power becomes P max divided by 2, then I should become I max divided by root 2. It is going to become I max divided by root 2. So when I becomes I max divided by root 2, power will become half. So if I say this is 100% of I max, So 1 by root 2 is actually 0.707. So about 70% of I max is the point where the power will become half. So this is I max divided by root 2, and this is also I max divided by root 2, and this is the variation of I with respect to the frequency. Now, if the current is 1 by root 2 times, originally Z at omega naught was R plus J multiplied by XL minus XC or XC minus XL. Either way is fine. So I can say plus or minus J of XL minus XC. So this is Z at omega naught, and at omega naught we said XL minus XC is 0. But at what point we are going to get I max divided by root 2? So Z has to be root 2 times R if current has to diminish to I max divided by root 2. So if the current has to become 1 by root 2 times, you should have the impedance to be root 2 times R. So I should have, if I had R plus or minus JR as the impedance, then in that case, I'm going to have root 2 times R, because R square plus R square square root, that is 2R square, square root of 2R square, that will become root 2R. So root 2R with an angle of 45 degrees, literally, plus or minus 45 degrees. This is going to be the impedance. So what we want is XL minus XC should be equal to R. That is the condition for having half power delivered to the resistance. When will half power be delivered to the resistance? Only when XL minus XC magnitude is equal to R. And we said that here capacitance will be dominating, whereas inductance will be dominating when the frequency is high. So I can say when omega is greater than omega naught, the impedance is going to be inductive. So I should say XL minus XC equal to R. And when the frequency is less than omega naught, the impedance is going to be capacitive. So we are going to have XC minus XL equal to R. Let us try to solve for both these frequencies. That is, if I may call this as some higher or upper frequency, and if I call this as lower frequency. So let us try to solve for both upper as well as lower frequency. So I should say omega L minus 1 by omega C equal to R, from which I should be able to write omega square LC. So I can simply say omega square minus 1 by LC, and I should also have minus R by L equal to 0. So this is corresponding to XL minus XC equal to R. Now, if you try to write what is the expression for omega from here, so that is corresponding to upper half power frequency. So omega U is going to be equal to, where is omega? Okay, so we have multiplied by omega, so we should have a omega here. So this is essentially minus R by 2L, rather plus R by 2L, root of plus or minus root of B square minus 4AC. So B square in this particular case is R square by 4L square minus 1 by LC. So this is going to be the upper half power frequency. So this is going to be the upper half power frequency. And if you look at this expression, if we use minus term here, it will can have a negative value, and negative value of frequency really does not make any sense. So only positive will be considered because the negative frequency does not make any sense. So we can write omega u equal to R by 2L plus R square divided by 4L square minus 1 by LC. Is it minus or plus? Because 4AC, so this should be plus. So plus 1 by LC, square root of this. So this is going to be upper half power frequency. So this is the upper half power frequency. Similarly, we should be able to look at lower half power frequency. So to derive that, we have to just say that XC minus XL equal to R. So I'm going to write 1 by omega C minus omega L equal to R. So let me write this as, let me take this omega also to the other side. So this is going to be R times omega plus omega square multiplied by LC. So I can divide it by L everywhere. And then I'm going to have plus 1 by LC or minus 1 by LC equal to 0. So the equation comes down to now omega square plus R by L omega minus 1 by LC equal to 0. So again, writing this as a quadratic equation solution. So omega L is going to be minus B, which is minus R by 2L plus or minus root of B square. That is going to be R square by 4L square minus 4AC. So that is going to be plus 1 by LC, 1 by LC, because divide by 4 will anyway cancel out with each other. So this is going to be lower half power frequency. Again, out of this plus or minus, we will use only positive will be, plus sign will be considered. So we are going to have in this particular case, omega L equal to minus R divided by 2L plus root of R square divided by 4L square plus 1 by LC. So if this has to have a positive value, necessarily R by 2L has to be smaller than the square root, the term under the square root. So R by 2L has to be smaller. That's all the more reason why we are using mainly only the plus sign here also. So in both the cases, we are going to use only the plus sign so that the frequency turns out to be positive. It cannot be negative. Now, the difference between omega H and omega L is generally known as the bandwidth. At least half the maximum power will be delivered to the resistance load. If you try to go for lower values of frequency than omega L and higher values of frequency than omega H, you are not going to get a good amount of power delivered to the resistance load at all. So bandwidth will come out to be R by L. This is going to be the bandwidth. So if a particular coil has a very large inductance as compared to the resistance, it will have a small bandwidth. That means the coil is going to be extremely selective. So if L is extremely high as compared to R, then bandwidth is small. That means the coil is going to be very selective. It is going to be really selective. That means it will not allow any power to be transferred to the load beyond a particular frequency range. So if I'm trying to look at this as omega naught, if I try to look at what is the kind of curve it has, it may have a curve which is really, really sharp. So it is going to rise steeply and fall also steeply. This is the way the power will be, as far as the power delivered to the load will be with respect to frequency. On the other hand, if I'm going to have R to be pretty large and L is not so large, in that case, I'm going to have a pretty flat kind of variation with respect to frequency, variation of power with respect to frequency. And also, if the resistance is large, I max is going to be equal to V divided by R. Because at resonant condition, the impedance is only resistive, nothing else. So because of that, I max will also be lower. If R is higher, then bandwidth is, then we are going to have bandwidth will be higher, but I max value comes down. That is going to come down. That is not going to be of perceivable value because the resistance itself is going to bring down the current drastically. Now, if we say this is R by L is bandwidth, which is beta, let us say, but we said that omega naught L divided by R, that is Q. So if I say that omega naught divided by Q, if we try to put this out, then this is going to be omega naught divided by omega naught L divided by R, which comes out to be R by L. So omega naught divided by Q is in one sense the bandwidth of any resonant circuit. So if I have a coil whose quality factor is very good, if the quality factor is good, that means the inductance is going to be high. In that case, the bandwidth is going to be low and the coil is going to be selective. So you can say in general, if the coil is selective, the power transferred to the load is also going to be good because I max again will be of a good value. Whereas if the bandwidth is larger, that means the quality factor of the coil will not be good, which means you are not going to see a good amount of Imax value, but the Imax value would have come down. So in that sense, bandwidth and the quality factor of the coil are inversely related to each other. Okay. So this is a very, very important point because you can't have the quality of the coil to be good and simultaneously you can't expect it to be really selective. That is one of the general remarks that we can make about series resonant condition. Now quickly we will take a look at parallel resonance circuit. So in parallel resonance circuit, what we are looking at is R, L, and C. All of them are connected in parallel with each other, and they may be excited with the help of a current source. So I may have a current source here, AC current source, which is specified by this. So this is going to be the current source, which is at variable frequency. And we are going to check at what condition resonance occurs and what do we mean by resonance for a parallel resonance circuit. So if I look at the overall impedance of the circuit, it's not very easy to calculate. Rather than that, we may write this as 1 by Z equal to 1 by R plus 1 by omega L. Of course, I have to write 1 by J omega L, and I had to write this as J omega C. So this is going to be the reciprocal of impedance for this parallel circuit, which we call as admittance. So the reciprocal of impedance is generally known as admittance, and it is indicated by the letter Y. And the reciprocal of resistance generally we call as conductance, which we indicate by the letter G. And reciprocal of reactance we call as susceptance. So this generally this we indicate by the letter B. So we will write Z equal to R plus JX, whereas Y equal to G plus JB. This is the way we write normally. So this is impedance, whereas this is going to be admittance. So if we look at resonant condition, in this particular case, under resonant condition, imaginary part of admittance vanishes. That is going to be equal to 0. So that means again, we are going to have 1 by J omega L is going to be equal to, rather plus J omega C equal to 0. Okay, so we are going to have 1 by omega L equal to omega C, which means omega is going to be equal to 1 divided by root LC. So this happens to be our resonant frequency. Again, this is going to be our resonant frequency omega naught, whether it is parallel resonance circuit or series resonance circuit. So under that condition, because our imaginary part completely vanishes, what we have got here is only the conductance, which is going to be G. So under that condition, we are going to have Y is going to be simply 1 by R, or this is going to be G at omega equal to omega naught. Okay, that means the admittance is going to be, admittance will be minimum at omega naught. So if I try to plot how the admittance varies with respect to frequency, let me just draw it like this. This is going to be omega naught, and omega increases in this direction. So I'm going to have, this is the variation of admittance. So admittance is minimum here. We normally write V divided by Z is going to be I. So in one sense, I should be able to write V multiplied by admittance is equal to I. Or I should say V is equal to I divided by Y. So for a given current, when the admittance is minimum, voltage is going to get very high value. So in this particular case, if I try to plot how the voltage varies, the voltage will be varying like this. This is going to be the variation of voltage with respect to frequency for a given current value when you are going to have varying frequencies. So this is going to be Vmax. This is going to be exactly Vmax. So this Vmax corresponds to resonant condition where the admittance happens to be minimum. So indirectly, in one sense, this is also the variation of impedance. The impedance peaks when you are going to have omega equal to omega naught. Okay. Whereas the quality factor in this particular case is exactly the reciprocal of. This is going to be the reciprocal of the quality factor in series resonant circuit. So in series resonant circuit, if we say it is omega naught L by R, this is going to be R divided by omega naught L. This is going to be the quality factor in the case of the parallel resonant circuit. So similarly, you would be able to calculate the bandwidth. So bandwidth also can be calculated by exactly finding out where Vmax divided by root 2 occurs. And similarly here also where Vmax divided by root 2 occurs, because we are going to have Vmax square by R divided by R. That is what is going to be our power delivered to the resistance. So from this, we should be able to get the bandwidth as well. So we are going to have, under this condition, we are going to have omega L, and this is going to be omega H. And then we should be able to calculate exactly what is the bandwidth corresponding to parallel resonance circuit as well. So let me try to do one numerical example for parallel resonance circuit. So let's try to do one problem for parallel resonant circuit. So the problem statement is somewhat like this. A parallel RLC circuit with a Q factor of 60 has a maximum impedance of 10 kilo ohm at 240 kilohertz. Calculate the frequencies at which half of the maximum power is delivered to the resistance. Okay, so this is what is being asked. So let us try to write the solution for this. First of all, if maximum impedance occurs at 240 kilohertz, we are going to have omega naught, that is the resonant frequency, is equal to 240 kilohertz. So if the resonant frequency is 240 kilohertz, then correspondingly, we can say 1 divided by root LC is equal to 240 multiplied by 10 power 3. And we are being asked basically to calculate what is the maximum, at what frequencies half of the maximum power is delivered to the resistance. Okay. So quality factor is already given as 60 and resistance is given to be 10 kilo ohm. So this is 10 multiplied by 10 power 3 ohms. That is what is resistance. And quality factor, which is actually R divided by omega naught L, that is given to be 60. So 10 multiplied by 10 power 3 is equal to 60 multiplied by 240 multiplied by 10 power 3 multiplied by L. So from which L can be solved for. Okay, so L turns out to be 694.44 microhenry. Okay, 10 power minus 6 Henry. Now from this L value and this equation, we can calculate what is C. So C value comes out to be 633.3 picofarad. So 10 power minus 12, that is picofarad. So that comes out to be this. Now, band width is generally defined by omega naught divided by Q. So omega naught is 240 multiplied by 10 power 3 divided by 60. So this is going to be 4 kilohertz. So 4 kilohertz happens to be bandwidth. So omega L is going to be 240 into 10 power 3 multiplied minus beta divided by 2. So that is 2 kilohertz. So this is going to be 238 kilohertz. And similarly, omega upper, that is going to be 240 multiplied by 10 power 3 plus beta divided by 2. So that is going to be 242 kilohertz. So this is going to be lower half power frequency, and this is going to be upper half power frequency. So these are going to be the lower and upper half power frequencies respectively. Okay. So now let us try to do a few problems from tutorial sheet 7. So let me try to take a look at tutorial sheet 7. And we will try to do a few problems from tutorial sheet 7. So tutorial sheet 7 is here. In problem number 1, it is given that a sinusoidal voltage of 6 sine 2t volts is applied to a 1 ohm resistance and 0.5 farad capacitance in series with each other. Find the voltage across the capacitor. So what is the voltage across the capacitor? That's what we need to determine. So this is problem number 1. So the source is 6 sine 2t, and we have a resistance and we have a capacitance. They are in series. Now what is being asked is how much is VC. So this is 0.5 farad and the resistance is 1 ohm. So one thing from this expression, we can say omega is 2 radians per second. 6 sine omega t, omega is 2. So 1 by omega c is xc. So that is going to be 1 divided by 0.5 multiplied by 2. That is going to be 1 ohm. So the overall impedance is going to be 1 minus J1 ohm, because the capacitive impedance will always be specified by minus J. The imaginary part will be negative for capacitor. So I'm going to have this as 1 square plus 1 square square root. So that is going to be 2 angle minus 45 ohm. This is going to be Z. Now, if I want to calculate the current is going to be, if I want the RMS value of current, the current RMS value will be 6 divided by root 2 divided by 2 angle minus 45 degree. So this is going to be 6 divided by 2 is 3. So 3 divided by root 2 angle 45 degrees is going to be the current that is flowing in the form of RMS current through this particular resistance and capacitance. I can write this as I is going to be, if I write this as I is going to be 3 sine, is this 2 or root 2? This is going to be root 2. So this is also root 2. So this is going to be 3 itself. I'm sorry, I goofed up while writing this Z value. So this is going to be 3 angle 45 degrees ampere. So this is going to be 3 times root 2 sine 2t plus 45 degree. If I want to write it in sinusoidal form, this is going to be the current. 3 root 2 sine of 2t plus 45 degree. This is what is going to be the current. So voltage across the capacitor is going to be 3 multiplied by 1 by omega c. That is going to be the magnitude. So that is going to be 3 multiplied by 1. So that will be 3 volts. That is the RMS value of the voltage. But if I want really that in terms of instantaneous value, that is going to be 3 root 2 multiplied by sine of 2t. And this is 1 by omega c angle 45 minus 45, right? This is going to be minus 45. So the voltage is going to actually lag behind the original current value. So this is going to be 1 by omega c minus j. So that is minus 90, not minus 45, minus 90. So this is going to be 2t plus 45 minus 90. So this is essentially I multiplied by jxc with a minus sign. I multiplied by minus jx. That's what I have written. So this is going to be 3 root 2 sine 2t minus 45 degree. So this is going to be the voltage across the capacitor. Okay, so this will be the voltage across the capacitor. So this corresponds to problem number 1. Let us now look at problem number 2. A current of 7.07 cos 500 t ampere flows through a certain device and the voltage across the device is 283 cos of 500 t plus 45 degree. So let me write that. So you are having, there is a circuit, voltage is 283 cos of 500 t plus 45 degrees. And current is 7.07 cos of 500 t. Please note that voltage is leading the current and it is leading by 45 degrees. So in all probability, this should be an RL circuit because voltage leads. Voltage is leading. Now, what is being asked is calculate Z real power and reactive power. So what are the impedance, real power and reactive power values? So let us try to do the solution. The first thing we need to do is to calculate what is the impedance. So impedance is voltage divided by current. So if we are using the peak value of voltage, we can also use the peak value of current. But if we are using RMS value of voltage, we should use RMS value of current. But we have to take into account the phase angle as well. So we are going to write this as 283 divided by 7.07 angle 45 degrees because this is leading. So this actually comes out to be the impedance, whatever is the impedance that is actually having a positive phase angle. So this will come in the form of R plus JX or Z angle positive phase angle. This is what is going to come up as. So this can be calculated. That's not a problem, right? You should be able to calculate it. Now, real power is going to be V RMS, I RMS, and cos of the phase angle between voltage and current. So in this particular case, the phase angle happens to be 45 degrees. The phase angle is 45 degrees. So this is going to be 283 divided by root 2 and 7.07 divided by root 2 and multiplied by cos of 45 degrees. So this is going to be real power in watts and this comes out to be 707.1 watts. So this comes out to be the real power. Now the reactive power is going to be V RMS, I RMS sine phi. And phi being 45 degrees, sine as well as cos of 45, both are 1 by root 2. So we should be able to write this as 283 divided by root 2 multiplied by 7.07 divided by root 2 multiplied by sine of 45. So this will also come out to be the same value as that of wattage. So this will be 707.1 VAR. This is going to be the volt ampere reactor. And the impedance, when I calculate, it comes out to be 33.66 angle 45 degrees. This happens to be the impedance. Okay. Any questions on this? So this is a pretty straightforward problem because the phase angle is already given and voltage and currents are already given. So you should be able to calculate the power directly, real power as well as reactive power. Volt ampere is 707 multiplied by root 2. That's all. So volt ampere, if I want, I have to simply say VRMS multiplied by IRMS. So I should simply have 283 multiplied by 7.07 divided by 2. This is going to be the apparent power. This will be the apparent power. Okay. Now let us try to do problem number 3. So the problem number 3 has the statement: a load connected across a 200 volts 50 hertz line draws 10 kilowatt power at a leading power factor of 0.7. Deduce the circuit elements, power and power factor. This is the first portion of the question. So 200 volts and 10 kilowatt of power. That is what is being said. So problem number 3. So it says the source is voltage is 200 volts, 50 hertz. And 10 kilowatt is the power. This is the real power at 0.7 power factor lead. So what are the circuit elements? So obviously, if the power factor is a leading power factor, this has to have R and C. So the elements have to be R and C. So in this particular case, let us try to work out the solution. So we can say P equal to VI cos phi. So P divided by cos phi is going to be equal to VI. So this is going to be 10 multiplied by 10 power 3 divided by 0.7 is going to be 200 multiplied by I, from which I can be deduced. So I comes out to be 71.43 ampere, but the power factor angle is going to be leading power factor, so plus cos inverse of 0.7. This is what is going to be the power factor angle. Okay. So the power factor angle comes out to be minus 45.57 plus 45.57. Sorry, because it is leading. So this is going to be 45.57 degrees ampere. This is the current. So I should be able to calculate Z as V divided by I. V is 200 angle 0 if we are taking voltage as the reference. And this is 71.43 angle 45.57. So this comes out to be 2.8 angle minus 45.57. So 2.8 cos 45.57 is R value, and 2.8 sine 45.57 is going to be XC value, which is equal to 1 by omega C, from which we should be able to calculate what is the capacitance. That should not be a major issue. Okay. Now the second portion of this question says, if the power factor has to be made unity from the supply viewpoint, what element should be connected across the single phase AC supply and what should be its value? So basically this circuit says we are going to have an AC voltage which is 200 volts, 50 hertz. And we are having R and C connected like this. So if you are having R here and C here, the current what we are taking here is a leading current. So if this happens to be the voltage, the current is leading. So the current is actually going like this. So this is going to be V and this is going to be I. Now what we want is the current should become a unity power factor current. They want the current to become a unity power factor current. So I need to have a current which would come out in such a way that probably it should have a value somewhat like this. If I can have a value somewhat like this, then I will be able to get a current which is in unity power factor condition. So this will be I final. And this will be the I addition, whatever I want to add. So if I add an element here, I have not shown what kind of element it is. If this is going to be I addition, and this is the original I value, now what I get here will be I final. And I want I final to be at unity power factor condition. So clearly this indicates that my I addition has to be lagging behind the voltage by 90 degrees. So this will be I addition. And if the current has to lag behind by 90 degrees as compared to the voltage, it has to be inductive. So this has to be inductive. So what I can try to do is to get this particular current's value. So I can try to decompose this current I along the voltage value. So I can call this as I cos phi and I can call this as I sin phi. So I should be able to get, or I can calculate the real power and reactive power, and I can insert an element here, an inductance here, such that it will be able to consume the reactive power that is generated by the capacitance. So let me first of all calculate real power and reactive power. And what we want primarily is the reactive power because we want to make it as a unity power factor condition. So let me try to calculate what is the reactive power. So reactive power is going to be VI sin phi. And what we got as the current was 71.43 ampere. And what we got as the voltage is 200. So 200 multiplied by 71.43. This has to be multiplied by sine of 45.57. This will give me what is the reactive power value. So this reactive power comes out to be 10.201 kVAR. This is the volt ampere reactive. Now this 10.201 kVAR has to be cancelled out by this reactance. So we can call this as V square divided by XL, which is very similar to V square by R is real power. Similarly, V square by XL will be reactive power that is consumed by an inductance. So we can call this as 200 square divided by omega L. That has to be equal to 10.201 multiplied by 10 power 3 VAR. So I should be able to calculate this as 200 square divided by 10.201 VAR equal to omega L. And omega is basically 2 pi multiplied by 50 because it is 50 hertz. 2 pi f multiplied by L, from which L value can be calculated. And L value comes out to be 12.5 milliamp. So this is one way of doing it. Otherwise, one more way of doing it is you can try to calculate what is I sin phi, and we can say I sin phi should be the current which will be drawn by this inductance. So this should be V divided by omega L. I sin phi magnitude I can calculate, and I can say that will be V divided by omega L, from which I should be able to calculate what is the value of L, because omega is known, I sin phi is known, and V is known. So only unknown quantity is L. So we should be able to calculate what is L without any difficulty. Okay. Now the next problem, problem number 4, is a 750 watt motor is connected to a single phase 120 volts 50 hertz power supply, and it draws a current of 10 ampere at 0.8 power factor lagging. Calculate the motor's efficiency, reactive power, and the losses incurred. Okay, so that is the first portion of the problem. So let us try to look at now problem number 4. So in problem number 4, the statement is a 750 watt motor connected to a 120 volts 50 hertz supply. Draws a current of 10 ampere at 0.8 power factor lag. First question is, what is the efficiency of the motor? That is the first question. Then the second question is, if the power factor is to be improved to 0.9 power factor lag, what should be the value of capacitor to be connected across the supply? Okay. So let us first of all try to understand what we mean by efficiency. So the efficiency is always defined for a motor or any other unit. It is defined as what is the output power divided by input power. That is what is the efficiency. Now output power is already given as 750 watts. And input power is going to be VI cos phi. And voltage is given as 120 volts. Current is given as 10 ampere. And power factor is 0.8. So we should be able to write this as 750 divided by 120, not 200, 120 multiplied by 10 ampere multiplied by 0.8. This is the efficiency. So this comes out to be 750 divided by 960. So this is 0.78125 or 78.125%. This is what is the efficiency. Okay. Now the second portion what is being given is the power factor has to be improved to 0.9 power factor lag. So the first thing we need to realize is the motor's power, what it wants to deliver as 750 watts, that is set in stone. And the efficiency is also set in stone. This is not going to change. So for a given motor power output, input power is a constant. It's not going to change. We are not going to improve the efficiency or anything. So real power is a constant at 960 watts. This is what it is drawing from the power supply. Now, reactive power at 0.8 power factor lag. That is going to be 960 divided by 0.8 will be the volt ampere multiplied by sine of cos inverse of 0.8, because cos inverse of 0.8 will be the phase angle and sine of that phase angle will give me what is the reactive power. So this happens to be volt ampere multiplied by cos phi, sine phi. Volt ampere multiplied by sine phi. And volt ampere is wattage divided by power factor. So this is essentially sine of phi. That's what we are trying to do. So this comes out to be, when I calculate the original reactive power, this comes out to be 720 VAR. So 960 is the wattage and 720 is the VAR, what we get. Now, so this is Q old. So let me calculate what is Q new. So this is reactive power at 0.9 power factor lag. That can be calculated as 960 divided by 0.9 multiplied by sine of cos inverse of 0.9. This will be the reactive power when the power factor is 0.9. So this comes out to be 464.95. So this is about 465 VAR. So this comes out to be 465 VAR. So if you may look at the circuit, I'm having a 120 volt source here. And here is the motor. The motor is represented by R and L because it is actually taking a lagging current. So we have R here and L here. Now, if we connect a capacitor here, it is going to take a leading current. So if I may draw the phasor diagram, this is the voltage. And what we have as the current is somewhere here. So this is going to be I. And this power factor, whatever we have, that is corresponding to 0.8, which is about 37 degrees. So the current is lagging by 37 degrees. If we want to improve the power factor such that we are going to have 0.9 as the power factor, that means I'm going to have essentially something like this. This is going to be the new power factor value. So this is going to be corresponding to 0.9 power factor, whereas this corresponds to 0.8 power factor. So the difference between these two will be having a current something like this. So this current, what has to be drawn by the capacitor. So this will be IC. So this is I volt and this black color current is I nu. So I volt plus IC will give me I nu. So this is going to be IC and this is going to be I volt and this will be I nu. So the difference between these two, Q volt and Q nu. So Q volt plus Q nu. This is Q to be supplied by C. So that is going to be 720 minus 465 bar. So this is going to be 720 minus 465. That is going to be the VAR. Now, you can say that reactive power of C will be QC, which is actually V square divided by XC, which will be V square omega C. So V square in this particular case is 120 square. Omega is 2 pi multiplied by 50, if it is a 50 hertz supply, multiplied by C, that will be equal to 720 minus 465, from which C can be calculated. C can be calculated without any difficulty when I have my reactive power like this. Okay. Now there are some problems which are associated with resonance. So let's try to do at least one of them. We had already done one problem with respect to parallel resonance when we just completed the topic of parallel resonance. So let us try to look at what is this particular problem. Design a series RLC resonance circuit to offer a bandwidth of 5000 radians per second with its resonant frequency being 200 kiloradians per second. The inductance available is 2.5 millihenry value with a Q factor of 65. So let us try to do this. So this is problem number 5. It says design an RLC series resonant circuit. Bandwidth has to be 5000 radians per second. This is the bandwidth. And omega naught is 200 multiplied by 10 power 3 radians per second. Kiloradians per second, and inductance available is 2.5 millihenry value with a Q factor of 65. So inductance is, what is the inductance value available? That is 2.5 millihenry with the quality factor of 65. Okay. Now, quality factor is defined by omega L divided by R. So this is omega naught L by R, which is 200 multiplied by 10 power 3 multiplied by 2.5 multiplied by 10 power minus 3. Okay, divided by R. So this is 200 multiplied by 2.5. So this is 500. So this is going to be 500 divided by R equal to 65. So from this you can say R is equal to 7.692 ohm. Please verify all the calculations. So this is going to be R equal to 7.692 ohm. Now, what is being asked is bandwidth has to be 5000 radians per second. So we can say bandwidth, which is equal to R by L in this particular case, right? So R by L, which is 7.69 divided by 2.5 multiplied by 10 power minus 3. Okay. So this comes out to be 3076.8 radians per second. It is not exactly 5000 radians per second. We are not getting a bandwidth of 5000 radians per second. We are getting a little less than that. We can calculate C as well. C can be calculated with 1 by root LC equal to 200 multiplied by 10 power 3, where L is equal to 2.5 multiplied by 10 power minus 3, from which C can be calculated. C comes out to be 0.01 microfarad in this particular case. So this comes out to be 0.01 microfarad. So please work out the other two problems. So if you may look at this tutorial sheet, there are problem number 6 and 7. Please try to work out those problems